SwayamPrabha. Digital India. Educated India.
Color Removing Technologies. Lecture number 9. Having understood that dyes are one of the main culprits in textile effluent, let us now look into deeper way of finding a solution for removal of the color from the textile effluent. Biotech approaches. Decolorization is achievable using one or combination of the following methods. One can use adsorption, filtration, precipitation, chemical degradation, photodegradation and biodegradation. Majority of the color removal techniques work either by concentrating the color into sludge or by partially breakdown or complete breakdown of the color molecule. Synthetic dyes such as azo dyes are resistant to microbial degradation under the aerobic conditions because dye stuffs are designed to be resistant to chemical fading and light induced oxidative fading. Some other water soluble reactive dye treatment systems based upon aerobic and anaerobic bacterial action are used to treat textile industry wastewater. Other factors involved in reducing the biodegradation of dyes include high water solubility and high molecular weight, which inhibit permeation through biological cell membrane. So, there are all kinds of methods available, but each method has its own for shortfalls, and therefore, we have to now see which of the biotech approach is most appropriate, whether adsorption, filtration, precipitation, chemical degradation, photodegradation or biodegradation, which one is more apt. Continuing with the biotech approaches, basic dyes are removed from wastewater by adsorption on the activated sludge. Acid dyes and reactive dyes, however, exhibit low adsorption values and thus pass through activated sludge processes unaffected. So, if it is working for basic dye, it is not necessary that it will work for other kinds of variety of dyes like acid dye or reactive dye. Aerobic system fail to remove many dye stuffs and may be subject to mechanical breakdown, expensive capital and running cost, susceptibility to shock loading, occupation of large areas of land and production of large quantities of sludge. So, there are when one is making aerobic digesters, then lot of space is required, while anaerobic processes which convert organic contamination into methane and carbon dioxide require less space. Treat waste containing up to 30,000 milligram per liter of COD have lower running costs and produce less sludge. So, if we compare the aerobic with the anaerobic system, these are the differences that one witnesses. Biotechnological solution offer almost complete destruction of the dye stuff with the co-reduction of biological oxygen demand, that is BOD, and chemical oxygen demand COD in a very less space. So, one advantage of using biotechnological solutions is that BOD and CODs are removed or lessened, and the space requirement for those equipment are very less as compared to the aerobic one. So, continuing with biological approach, we will have a little overlap with the previous lecture, because we are now looking primarily on the color removal technologies. So, some of the things which we have mentioned, like activated sludge processes, trickling filters, SBR, and wetland, construction wetland, all these will be repeated again. Biological approaches to treating textile effluent involve using living organisms like bacteria, fungi, algae, or plants to break down or remove pollutants from the wastewater. Here are some commonly used biological methods, and we have learned that in the previous lecture. Activated sludge process. This is a widely used biological method where microorganisms, mainly bacteria, break down organic pollutants in the presence of oxygen. The effluent is mixed with activated sludge, which contains a diverse population of microorganisms in an aeration tank. The microorganisms consume organic matter, converting it into carbon dioxide, water, and biomass. Trickling filters. This also we have studied in the previous lecture. In this method, wastewater is trickled over a bed of porous material such as rock or plastic beads, where microbial biofilms develop. The microorganisms in the microfilm or biofilm degrade organic pollutant as the water passes through it. Constructed wetlands. This involves using natural or artificial wetland ecosystem to treat wastewater. Plant microorganisms and the wetland substrate work together to remove contaminants through all the three processes: physical, chemical, and biological processes. The roots of the wetland plants provide surfaces for microbial growth and help in nutrient uptake. So, it is a very synchronized system where all the microorganisms, even the plants in the constructed wetland, whether it is natural or it is artificially made, work together in order to break down these pollutants of the wastewater. Bio-augmentation. This method we had not discussed, so this is a new idea which you have to understand in this lecture. This method involves adding specific strains of microorganisms to the wastewater to enhance the degradation of pollutants. These microorganisms are selected from their ability to metabolize target contaminants efficiently. So, here there is a planned strategy where certain microorganisms which have been identified to break down certain organic pollutants are chosen. So, that is why the name bio-augmentation. Phytoremediation, this also we had not covered in the last lecture, is a new phenomena. Certain aquatic plants have the ability to absorb and accumulate pollutants from water. Phytoremediation involves using these plants to remove contaminants from textile effluent. The pollutants may be stored in the plant tissue or transformed into less harmful substances. So, first is the absorption into the plant, and then they may be able to metabolize it or make it into less harmful substances. Algal treatment. Algae can be used to treat textile effluents by utilizing their ability to photosynthesize and absorb nutrients and pollutants. Algal ponds or reactors are used to cultivate algae, which can remove nutrients like nitrogen and phosphorus as well as organic pollutants from the wastewater. So, even algal treatment is a new phenomena which we are learning in this lecture. Anaerobic digestion we had covered in the previous lecture. In anaerobic condition without oxygen, certain bacteria break down organic matter in the effluent, producing biogas, mainly methane, as a byproduct. This process can be used to treat high strength organic wastewater and produce energy simultaneously. So, it is an advantageous process where the byproduct is very useful. Each of these methods has its own advantages and limitation. Depending on the factors such as composition of the effluent, treatment objectives, cost and available space. Integrating multiple treatment approaches is a treatment train that can often improve overall efficiency and pollutant removal. So, sometimes one method can work and another time a chain of methods one after the other can work for the removal of the pollutant. At the moment we are concentrating on removal of the color which comes from dyeing or dyes and pigments, which pigments are used in printing. So, we will be concentrating on two areas, dyes and pigments, which are the cause for the color of the textile effluent. The technology for simultaneous removal of color, organic substances and heavy metal pollutants from textile dye wastewater consists of three basic steps: hydrophobic precipitation of ionic dyes by proprietary surfactants, that is, some of them are special polymers, self association to form large size aggregates, and third is separation of dye aggregates from solution by filtration or flotation. So, these three methods are very important and are useful in removal of the dyes. The mechanism underlying this process is based on chemical reaction, charge neutralization and hydrophobic coagulation. That means it makes it a coagulant which is not water soluble. Metal contaminants in textile dyeing effluent which are present in complex form cannot be removed by conventional precipitation or reduction methods. So, color and organic pollutants removal from textile effluent can be achieved through various treatment methods, both physical and chemical. Here are some commonly used techniques, and we had learned this, that we had learned the term coagulation and flocculation, but I had not mentioned as to what are the coagulants and what are the flocks that are added. Chemical coagulants such as aluminum sulphate, that is alum, ferric chloride or polyaluminum chloride, that is PAC, can be added to the effluent to destabilize colloidal particles and organic matter. Subsequent flocculation promotes the aggregation of destabilized particles, forming larger flocks that can be easily removed by sedimentation or filtration. Activated carbon adsorption. Activated carbon is known to be a good decolorizer. Now, how does it work? Activated carbon has a high surface area and absorptive capacity, making it effective for removing organic pollutants, colorants and odorous compound from textile effluents. The effluent is passed through a bed of activated carbon, where contaminants are adsorbed onto the carbon surface. Membrane filtration. We had fleetingly talked about membrane filtration as one of the techniques for the processing of textile effluent. Now, we will see that in a little more detail. Membrane processes such as ultrafiltration UF, nanofiltration NF and reverse osmosis RO can effectively remove suspended solids, colorants and organic molecules from textile effluents by physical filtration through semi-permeable membranes. What is semi-permeable membrane? A membrane which can allow certain molecular weight size passage through the membrane pores and not bigger sizes. So, it is semi-permeable, it permeates only smaller molecules and not larger molecules. These processes offer high removal efficiency, but may require pre-treatment to prevent membrane fouling. Biological treatment. Biological treatment method such as activated sludge, trickling filters, constructed wetlands utilize microorganisms to degrade organic pollutants present in the textile effluent. The microorganism metabolize organic matter, converting it into carbon dioxide, water and biomass. Some microorganisms can also metabolize specific dye molecules leading to color removal. So, this is one very good method of removal of color. Advanced oxidation processes. We had fleetingly seen the mechanism of AOPs. AOPs such as ozone oxidation, UV hydrogen peroxide treatment and Fenton's reagent hydrogen peroxide with iron catalyst generate highly reactive species such as hydroxyl radical that oxidize and degrade the organic pollutants and colorants present in the textile effluent. They are very powerful oxidizing agents and therefore, they can work on the pollutant very effectively. These processes are particularly effective for treating recalcitrant organic compounds and colorants, which are not easily breakable, are called recalcitrant. Electrocoagulation. Electrocoagulation involves the use of electric current to destabilize and coagulate suspended particles, organic matter and colorants in textile effluents. Metal ions generated at the electrode form insoluble hydroxide precipitates which trap contaminants and facilitate their removal by sedimentation or flotation. So, many new methods we have come across and these are all applied to remove color and organic pollutant from the textile effluent. Chemical oxidation. Chemical oxidation methods such as hydrogen peroxide oxidation, potassium permanganate KMnO4 oxidation and chlorine dioxide ClO2 oxidation can be employed to degrade organic pollutants and colorants in textile effluents. These oxidizing agents react with organic molecules, breaking them down into simpler, less harmful compounds. So, earlier we had studied about ozone, we had studied about hydrogen peroxide, but we had not studied about KMnO4. And so, this is a new learning that chemical oxidation can also be carried out by powerful oxidizing agent KMnO4. Combined treatment processes. Combining multiple treatment processes in a treatment train can enhance the overall removal efficiency of colorants and organic pollutants from the textile effluent. For example, a combination of coagulation flocculation followed by biological stream or AOS can effectively treat complex wastewater streams. The selection of appropriate treatment method or combination of method depends on factors such as composition of the effluent, desired treatment objectives, site specific conditions and regulatory requirement. Not to forget that regulatory requirements are what are the driving force for such removal of color and organic pollutants from the textile effluent. Now, if we make a comparison of conventional treatment methods, in the ozonation, the limiting factor is the rate at the interface between gas and liquid, and that a packed column gives more efficient use of ozone. There is a stoichiometric relationship between the amount of ozone and the dye consumed. So, here large amount of ozone has to be used because it is taken into stoichiometric equivalence. Oxidation with peroxide and UV causes removal of color undoubtedly, which increased proportionally with UV intensity and concentration of peroxide. Microfiltration removes much smaller molecules including electrolytes. Electrochemical color removal from wastewater occurs by combination of adsorption and chemical reduction. So, a comparison of some conventional treatment processes commonly used in textile effluent treatment is given here. Physicochemical treatment like coagulation and flocculation. What are the advantages and what are the disadvantages? This process involves the addition of chemicals such as alum, ferric chloride or polyaluminum chloride PAC to destabilize suspended solids and organic matter. Flocculants are then added to promote the aggregation of particles, facilitating their removal by sedimentation or filtration. The advantages are effective removal of suspended solids, colorants and certain organic pollutants, relatively simple and widely applicable. Disadvantages: high chemical usage, generation of sludge requiring disposal, limited effectiveness for treating complex organic pollutants. Biological treatment. What are the advantages and what are the disadvantages? Activated sludge process. In this method, microorganisms metabolize organic matter present in the effluent under aerobic condition. The effluent is mixed with activated sludge in an aerated tank and the microorganisms convert organic pollutants into carbon dioxide, water and biomass. Advantages are that effective for degrading organic pollutants, reduced chemical usage, lower sludge production compared to physicochemical methods. Disadvantages: longer treatment times, sensitivity to fluctuations in influent characteristic may require additional treatment for color and recalcitrant pollutants. So, as we see that there are advantages and there are disadvantages in every method that have been tried out for removal of color and organic pollutants in the textile effluent. Adsorption. Activated carbon. Activated carbon adsorbs organic molecules, colorants and odorous compound from the effluent due to its high surface area and absorption capacity. The advantages are high removal efficiency for a wide range of contaminants, including colorants and organic pollutants. Disadvantages: high operational cost, frequent carbon replacement or regeneration required, may not be suitable for continuous treatment of large volume of effluent. So, one or the other method is better than the previous one, but it too has its own disadvantages, and therefore, very carefully the processes have to be selected. Membrane processes: ultrafiltration, nanofiltration, reverse osmosis. Membranes processes physically remove suspended solids, colorants and dissolved organic pollutants from the effluent by filtration through semi-permeable membrane. So, this is the fundamental of that. Now, the advantages are high removal efficiency, compact footprint, can produce high quality treated water suitable for reuse. So, the advantages are very good, whereas disadvantages is the high energy consumption, especially for reverse osmosis, and that we have seen that the ROs that are fitted in our homes also have the same fundamental. Membrane fouling requiring maintenance and cleaning, sensitivity to fouling by organic matter and scaling by inorganic matter, and that is a serious problem with these membrane filters. Chemical oxidation, ozone treatment, hydrogen peroxide with UV, these advanced oxidation processes AOPs generate highly reactive species such as hydroxyl radical, that is O.OH, that oxidize and degrade organic pollutants and colorants. It is highly reactive. The hydroxyl radical OH dot is highly reactive. The advantages are effective for treating recalcitrant organic pollutants and colorants, can be combined with other treatment processes. Disadvantage, high operational costs, safety concerns especially for ozone, may require post treatment for residual oxidants. So, there is always a chance that some of the ozone may remain unreacted. So, for removal of color and organic pollutants from the textile effluent, this process has following advantages over conventional method. The most effective, the more cost effective, much shorter retention time, operative at high temperatures, no sludge disposal problem, high quality water. So, if we have an advantage of this type by any method, then that method will be very, very superior, where it will be cost effective, will require less time, can be operated even at high temperature and no sludge generation, and the output of the water quality would be very good. So, continuous ozonation process is one of the methods which is adapted at many mills. This treatment is conducted in packed columns to continuously ozonate reactive dyes in spent dye bath water by using double packed column, each having 2.8 liter capacity excluding packing. Both ceramic and glass rashing ring packed columns can be used. Color removal and efficiency of ozone utilization improves with column packing due to improved contact. The color removal increases as dwell time increases. Change in pH from 2 to 11 or temperature changes from 25 degrees to 500 degrees had minimal effect on dye decolorization with ozone. So, that means it is not temperature dependent, but definitely it is pH dependent. Maximum efficiency of ozone treatment is achieved by contracting the ozone enriched gas stream with the most concentrated dye solution. Ozonation of spent reactive dye bath water. The decolorization treatment is conducted using a single packed column of 2.8 liter capacity at a flow rate of 160 ml per minute, which gave a dwell time of 17.5 minutes in the column. The ozone flow is kept 9 grams per hour at 1.1% concentration in oxygen. Color removal was almost 70 to 99% obtained depending on the depth of shade of the dyed material. The pH decreased during ozonation, and addition of caustic as soda was needed as catalyst for subsequent dyeing. So, what happens is that when this ozonation is carried out, one needs to continuously monitor the pH, and that is done by adding the caustic soda. Ultraviolet light and hydrogen peroxide treatment of textile effluent, and we studied this in the previous lecture, but we will see a little more detail in this lecture. Ultraviolet light combined with hydrogen peroxide treatment is an advanced oxidation process AOP commonly used for the treatment of textile effluent. Here is how the process works. UV radiation. The effluent is first exposed to UV light. UV light is capable of generating highly reactive species called hydroxyl radical through the photolysis of hydrogen peroxide. So, H2O2 breaks into 2 OH dot. Hydrogen peroxide addition. Hydrogen peroxide is added to the effluent either before or during UV radiation. Hydrogen peroxide serves as a source of hydroxyl radical when activated by UV light. These hydroxyl radicals are strong oxidizing agents capable of breaking down complex organic pollutants present in the effluent. So, this mechanism we had seen in the last lecture also, but to emphasize that how important the mechanism becomes, because it is a very simple chemistry. UV light is just doing photolysis of hydrogen peroxide and 2 hydroxyl radicals are formed. But these hydroxyl radicals are great oxidant for organic pollutants. The hydroxyl radical generated in the reaction are highly reactive and can rapidly oxidize a wide range of organic compounds present in the effluent. These radicals attack the chemical bonds of organic pollutants, breaking them down into smaller, less harmful molecules such as carbon dioxide, water and simple organic compounds. Degradation of dye and organic pollutants by the use of UV hydrogen peroxide process effectively degrades various contaminants found in the textile effluent, including dyes, solvents, surfactants and other organic pollutants. So, it is not that this hydroxyl radical can only work on the dyes and organic pollutants, it works on other surfactants, solvents and other organic pollutants as well. Post treatment. After UV and H2O2 treatment, the effluent may undergo additional treatment steps such as sedimentation, filtration or biological treatment to remove any remaining suspended solids or residual contaminants. Monitoring and optimization. As I mentioned in the previous lecture also, in all processes, monitoring and optimization is a must. The efficiency of UV and hydrogen peroxide process depends on factors such as concentration of hydrogen peroxide, UV light intensity, reaction time and the characteristic of the effluent. Continuous monitoring and optimization of these parameters are necessary to achieve the desired treatment performance. Environmental consideration. While UV H2O2 treatment can effectively degrade organic pollutants, it may also generate intermediate byproducts that need to be carefully managed to prevent environmental harm. Proper disposal or treatment of these byproducts is essential to ensure that the overall environmental impact of the treatment process is minimized. So, the whole idea is that we should choose a method which will not have any adverse effect on the environment. Overall, UV hydrogen peroxide treatment offers an efficient and environmentally friendly solution for the treatment of textile effluents, helping to reduce the environmental footprint of the textile industry and protect water resources. Primary UV peroxide treatment made in batch reactor. The reactor consists of 2-liter graduated cylinder in which is immersed a quartz tube holding a 32-inch low intensity UV lamp. The lamp produces radiation at wavelength range of 189 to 254 nanometers, of which 90% is at 254 nanometer. Samples of the dye solutions are checked periodically using a spectrometer for estimating the rate of decolorization. A typical example, water soluble dyes such as direct dye, acid dye or reactive dye, where normally the spent dye bath has higher amounts of color present, have been studied for the effect of pH using 0.02 gram per liter direct blue 25 and 0.5 gram per liter hydrogen peroxide 50% strength. Maximum rate of color removal is achieved when dye concentration is 0.05 at the peroxide concentration of 3.0 gram per liter. Optimum peroxide concentration is 3.0 gram per liter at the highest dye concentration of 0.3 gram of reactive blue 21 dye. So, various dyes have been tried out, and these dyes could be acid dyes, they could be direct dyes, they could be reactive dyes, and they work very well on all these 3 types of dye with very low concentration of peroxide. Maximum required is 3.0 gram per liter of strength 50%. In case of water insoluble dispersed dyes, the rate of decolorization is slow. For dispersed orange 3 and azo dye, 80% decolorization is obtained in 1 hour at 0.02 gram per liter dye concentration and 0.5 gram per liter peroxide with 9 watt per liter UV radiation. So, it does not work that effectively for dispersed dye as what it works for direct dye, acid dye and reactive dye. For dispersed red 60 and anthraquinone dye, only 5% color removal is obtained in the same period. So, it is even worse in the case of dispersed red 60. The rate was 3 order of magnitude lower for water insoluble dyes. This is much below the results achieved by biotechnological treatment. Hence, we can say that for insoluble dyes, ultraviolet light and hydrogen peroxide treatment methods are not the optimal method for carrying out the color removal. Coming to anaerobic digestion. Anaerobic digestion, again and again we are learning in a little deeper manner in each lecture. Anaerobic digestion of textile effluent involves treating the wastewater in the absence of oxygen using specialized microorganisms to break down organic matter. Here is how the process typically works. Pre-treatment. Before anaerobic digestion, pre-treatment step may be necessary to remove large solids, adjust pH or remove toxic compounds that could inhibit the digestion process. This ensures optimal condition for the anaerobic microorganisms, because unless and until the large particles are removed, the pH is made equalizing to the microorganisms' existence, and all the major toxins that needs to be removed are there, then this process works very well. Digestion process. The pre-treated textile effluent is then introduced into an anaerobic digester. This can be a batch or a continuous process depending on the design of the system. The digester is typically a sealed vessel where anaerobic microorganisms thrive in the absence of oxygen. So, as the name suggests, again and again I am mentioning, anaerobic digestion requires no oxygen. It is in the absence of oxygen that these microorganisms thrive, and they actually metabolize the organic pollutants and dyes. Microbial activity. Within the digester, complex organic compounds present in the textile effluent are broken down by anaerobic bacteria into simple molecules such as volatile fatty acids, carbon dioxide and methane. These microorganisms work in several stages with different groups of bacteria breaking down various components of the organic matter. So, it is not a very simple chemistry that is happening. Biogas production also takes place simultaneously, as I had mentioned in the previous lecture, in the process of anaerobic digestion. One of the significant byproduct of anaerobic digestion is biogas, which is primarily composed of methane and carbon dioxide. This biogas can be captured and used as a renewable energy source for heat and power generation, reducing the reliance on the fossil fuels and providing an economic incentive for the treatment process. Effluent treatment. As the organic matter is digested, the effluent becomes stabilized and undergoes a reduction in organic load. The treated effluent may still contain some residual pollutants, but the concentration is significantly lower compared to the untreated effluent. Post-treatment. Depending on the quality requirements for the discharge or reuse, post-treatment steps such as aerobic treatment, filtration or chemical treatment may be necessary to further polish the effluent and meet regulatory standards. So, it is possible that further the effluent is treated, post-treated with chemical treatment or aerobic treatment or filtration, so that it matches with the regulatory standards. Advantages of aerobic and anaerobic digestion. We have seen the advantages in the previous lecture, but in this one we will be elaborating furthermore. Anaerobic digestion of textile effluent offers several advantages, including energy recovery in the form of biogas, reduction in organic pollutants and potential cost saving compared to aerobic treatment methods. So, there are threefold advantages. First, it is giving energy through biogas formation. Second, it is reducing drastically the organic pollutants, which is the main objective, and also there is a potential cost saving as compared to aerobic treatment methods. However, the process requires careful monitoring and control to maintain optimal condition for microbial activity, because if the microbial activity has to thrive, then the atmosphere and the parameters have to be congenial for that, and certain contaminants or inhibitors in the effluent may affect digestion performance. So, it is possible that if one or two contaminants are such that will kill the microbe, then the whole process will not go further. Overall, anaerobic digestion can be an effective and sustainable method of treating textile effluent while mitigating environmental impact and resource consumption. So, overall we can say that anaerobic digestion is advantageous for removal of color and organic pollutants. Azo-dye degradation with the combination of anaerobic and aerobic treatment processes. Because as I said, azo dyes are difficult to break, and because of the N double bond N group present, which is the azo group, decolorization of azo dye during biological effluent treatment can involve adsorption of the cell biomass and degradation of azo bond reduction during anaerobic digestion. Degradation forms aromatic amines which may be toxic and recalcitrant to anaerobic treatment, but degradation they are degradable aerobically. Methods for quantitative detection of substituted aromatic amines arising from azo dye cleavage complex. A simple qualitative method based on high performance liquid chromatography and ultraviolet technique is used to investigate degradation and whether the amines generated are successfully removed by aerobic treatment. So, even simultaneous monitoring is done, and that is how one can know that whether it has done its performance or not. Aerobic treatment and anaerobic treatment gave significant decolorization and respiration inhibition tests showing that the anaerobic effluent had an increased toxicity due to azo dye degradation. Polar and UV absorbing compounds generated are removed or converted to highly polar compounds aerobically. So, lot of chemistry keeps happening in this condition where there is they can be identified through a very simple but qualitative method of HPLC UV method. Anaerobic digestion of reactive dyes are difficult to remove from the textile wastewater due to their solubility, and they pass through conventional aerobic biological effluent treatment system and enter the receiving water body. Reactive dye bath effluent is discharged into primary digester containing sludge. The overflow is monitored for color, sodium and sulphide concentrations. Reactive dyes are capable of forming covalent bonds between the dye molecules and the fiber. 10 to 50% of the initial dye load will be present in the dye bath effluent, giving rise to highly colored effluent. The target compound azo dye is not biodegradable by the microorganism. Instead, this dye acts as an oxidizing agent for the reduced flavin nucleotides of the microbial electron transport chain and is reduced and decolorized concurrently. Therefore, a source of reduction resulting from the degradation of a suitable carbon source is essential to ensure decolorization and maintain the anaerobic population. So, a lot of chemistry keeps happening even at the anaerobic digester. The carbon source requirement was fulfilled by glucose in the laboratory system. However, for large scale application, primary and secondary sludge are the carbon source for anaerobic digestion. The carbon is converted to methane and carbon dioxide, during which process electrons are released. The electrons react with the dye by reducing the azo dye bond and thus causing decolorization, because once the azo linkages break, the dye is no more a dye, it becomes primary amines, and these amines are not colorless. not having any color. Aerobic digester. There are 4 primary anaerobic digester and 4 secondary digester, each having a volume of approximately 1.34 megaliter. The primary digesters are heated to about 37 degrees and have a sludge residence time of between 25 to 30 days. The secondary digesters are not heated and have a much longer residence time. There is one method that we have developed in our laboratory for removal of color and treatment of the dye effluent using a graft copolymer of moringa seed with acrylamide, and this was treated for dye effluent. The grafted copolymer was treated for its efficiency for metal removal, that is chromium 6, and color, that is associated with chrome 6, from tannery effluent, and for color removal from textile effluent using standard spectroscopic methods. The efficiency of the color removal was found to be 89% in just 15 minutes. Similar results were obtained for efficient metal removal from the textile effluents. The prepared graft polymer could be used also to remove color from dye effluents. 89.09% of the color was removed in 4 hours from the dyes present in the industrial effluents. Desorption studies were conducted to restore the biomass as a function of concentration of different desorption reagents. So, this graft copolymer of moringa seed with acrylamide was used for treatment of dye effluent and is an innovative approach with potential environmental benefits. Here is how the process could work. Selection of moringa seeds. These moringa seeds are chosen for their nature being natural coagulant properties. Moringa seeds contain cationic proteins that can bind with negatively charged particles, including organic dyes found in effluent. Preparation of moringa seed extract. The seeds are typically crushed and soaked in water to extract the cationic protein. This extract acts as a neutral coagulant. Graft copolymerization. Acrylamide, a commonly used monomer in polymer chemistry, is polymerized in the presence of moringa seed extract. This process forms a graft copolymer, where acrylamide chains are covalently bonded to the protein molecules of the moringa seed. This was characterized whether such a synthesized graft polymer was formed or not. So, the synthesized graft copolymer was characterized to determine the chemical structure, molecular weight, and efficacy as a coagulant for dye removal. Treatment of dye effluent. The graft copolymer is then used in the treatment of dye effluent. When added to the effluent, the copolymer acts as a coagulant, binding with the dye molecules and other impurities, forming larger aggregates that can be easily removed by sedimentation or filtration. Performance evaluation. The efficiency of the graft copolymer in dye removal is evaluated by measuring parameters such as color removal, chemical oxygen demand, that is COD reduction, and turbidity removal. The effectiveness of the treatment is compared with conventional coagulants and flocculants. Environmental impact. Compared to synthetic coagulants and flocculants, the use of moringa seed based graft copolymer offers environmental benefits. Moringa seeds are natural, biodegradable, and readily available, reducing the reliance on synthetic chemicals and minimizing environmental pollution. Optimization. the process parameters including the ratio of moringa seed extract to acrylamide, reaction condition and dosage of the copolymer are optimized to maximize dye removal efficiency and minimize cost. Overall, the graft copolymerization of moringa seed with acrylamide present is a sustainable and effective approach for treating dye effluent, offering both environmental and economic advantages. So, this particular work that we did with moringa seed making a graft copolymer with acrylamide really worked very well, both for heavy metal removal, particularly chrome 6, which is a hazardous toxin, and the color of the textile effluent. Now, showing the capacity, if we are using only the color removal efficiency of just the moringa seed, it shows 74%, but when it is grafted with acrylamide, then it shows 89.09%, which is that it can remove color very well. In conclusion, we can say the selection of most suitable treatment process depends on factors such as composition of the effluent, treatment objectives, available resources and regulatory requirements. Often, a combination of different treatment processes in a treatment train is employed to achieve the desired effluent quality. Integrating physicochemical, biological and advanced treatment processes can enhance overall treatment efficiency and ensure compliance with regulatory standards. Additionally, ongoing research and innovation in treatment technologies are essential for developing more sustainable, cost-effective solutions for textile effluent treatment in future. So, which means that we are progressing towards a time where research is needed to find better methods than the existing methods. Some of the methods are very good, but as we saw that whether it is anaerobic digester or whether it is treatment with some any of the wetland construction wetland or trickling filters, each of these methods have their set of advantages and disadvantages. So, one has to optimize and see what is the pollution load in the textile effluent and how it can be mitigated either by one method or by combination of methods. So, that is how we come to a conclusion that these methods have to be relooked very carefully, looking at the cost effectivity, looking at the space requirement, looking at the influence, chemical composition. The methods have to be selected in a manner that it works, that technology works for that particular textile effluent effectively, so that it meets the regulatory standards. Otherwise, the whole process, we cannot just start with anything and everything. So, here I would like to say that in conclusion, we need to take a very serious look and try to understand. Having understood all the methods, we now have to decide which one is good, and for that matter it is very important to first get the effluent tested for its dye content, color, pH, turbidity, COD, BOD. These are parameters which need to be tested first. Based on that, the strategy of remediation should be planned. So, with this we have come to an end of this lecture. Thank you.